here we are at the last of our fundamental skills, drawing scientific graphs. So when we make a scientific graph, it shows us the relationship between the manipulated variable and the responding variable. Something very important on this is that our manipulated variable is always along the x-axis and our responding variable is always on the y-axis. Now, if you don't remember what a manipulated and responding variable is, go look it up. Manipulated being the thing that you are changing and the responding being the response to that change. So all graphs have to include 5 pretty basic things. So number 1, they should have a title that lets you know what the manipulated and responding variable is. So y as a function of x, fantastic title. Do not make any assumptions with that. Do not make any inferences from your graph. It's just manipulated and responding. You need to label your axes with appropriate units. You need linear scales on each axis, and you need to make sure that those scales will allow your data to fill at least half of the graph. You don't want a little graph that's way off into the corner, and you don't want to be going off of your graph either. So it needs to fit on your piece of graph paper, on your grid, and it needs to take up about at least half. Those linear scales, what we mean by linear scales is you can't go up by like 3, then 5, then 15, then 19, then 22. That's not going to show you any kind of relationship. It's really good to go up by ones, so 1, 2, 3, 4, 5, go up by twos, 2, 4, 6, 8, 10, go up by fives, 5, 10, 15, you get the idea. You need to correctly plot the data and cross out any outliers. So outliers are things that don't really fit with the data. They may have been mistakes. Oftentimes you see them right at the very beginning and right at the very end of experiments. If everything looks like an outlier, maybe there's no relationship between manipulating and responding. Maybe something else went wrong, but usually just maybe 1, maybe 2 data points. Again, a lot of times towards the beginning and the end of your data that don't really fit with the rest. And then the last thing that you need is a line of best fit which represents the trend in the data for all linear data. So that's a straight line, and that's most of what we're doing in Physics 20. You want to use a ruler to represent that. You don't want to just freehand it. So you need a straight edge or a ruler. Cool. Now, the slope of that line of best fit actually tells us some really important things about the data. And we'll be exploring those things as we go through this course and as we go through Physics 30 as well. So you need to know when we're calculating the slope, and this comes from y is equal to mx plus b, our slope is the change in our responding variable per unit of the change of our manipulated variable. And that might sound pretty confusing, but it's the rate at which y is changing as x changes, right? So x versus y, and it tells us how quickly y is changing, in other words. Kind of give you a whole bunch of different ways to look at that. So let's go through and let's test out a quick example of this, and let's figure out with our formula for slope how exactly we can deal with this. So our example, create a velocity time graph for the following data, determine the slope of best fit, including units. Cool. Okay, so first and foremost, we should mention that our manipulated variable, which is x, is typically listed first in graphs, and our responding variable, or sorry, charts I mean, is typically listed second. For physics, we will see that time is our manipulated variable very, very, very often, and we know that our manipulated variable has to go on our x-axis. So we put time, we make sure we include the units for that. Our velocity is our responding variable, so we put it on our y-axis, we include units, and then we would need an appropriate title, so I'm going to put it as velocity as a function of time. Very, very nice. Very good. Okay, next step. So we can't really plot the data yet, so next step we need to figure out what an appropriate scale would be for this. So as I go through, it looks like time needs to go up to 10 seconds, and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, wow, that looks amazing. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then finally 10 seconds. Perfect. I think velocity might be a little bit more challenging. So it's got to go from essentially 0, and I know 0 is not a data point, but it's really nice to include 0. So we are going to start at 0, 0. And it has to go up to 2.5. So, excuse me. Let's think about this for a second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I went up by 0.1, I think I'd run out of space. Let's try it if I go up by 0.2. So 0.2, 0.4, 0.6, 0.8, 0.10. I might be running out of space here too. I definitely am, so we got to rethink that one a little bit. Where's the, shoot, got to go back to the felt pen. Okay, so I think I got it here. Let's think this one out. Oops, that's an eraser, not a pen. So I'm gonna go 0.5. Yeah, so confusing myself here. Don't worry about it too much. So 0.5, 1, 1.5, 2, 2.5, and then I'm just going to put it up to 3, 3.5, et cetera, et cetera. Now, the rule of thumb is it needs to take up at least half of the graph, which we are taking up, well, exactly half of the graph with our data. So we can make that work. We can absolutely work with that. So let's go through and let's check it out. My first one, I'm going to do this in green. So it's 0, 0. At a time of 0, I've got a velocity of 2.5. Excellent. There it is. Very nice. At a time of 2.0, I've got a velocity of 2.4. So 2 seconds, we are at 2.4. So just ever so slightly below that. Let's see, at 4 seconds, we are at 1.5. 4 seconds. There we go, 1.5. At 6 seconds, we're at 0.9, so just slightly below there. And then let's see, 8 seconds, we're at 0.6. So a little bit above the 0.5 there, and we're kind of estimating. And in 10 seconds, we're at 0.1. So I'm going to estimate that to be very, very close. Perfect. So this looks like a pretty nice, neat straight line. What I need to do now is I've plotted my data, I've got my title, I've got everything there. Let's go through and let me get a straight line drawer. For you, that would be a ruler or a straight edge. So it looks about like there. I don't think I have many outliers in this case because they all follow pretty close to the pattern. So I think this looks pretty good right here, actually. I might wiggle it around a little bit. And this is the thing about line of best fit. You kind of got to wiggle it and move your ruler up and down a little bit until you get to a place where you feel that you are confident with things. I think that might be good. Now the line of best fit, does it have to go through the origin, 0, 0? No, and in this case, I don't even know how you would. Does it have to touch any of your data points? No, right? But it needs to be as close to as many data points as possible to show that general trend of all of your data points. So now that we've got a line of best fit, we need to take 2 points off of our line of best fit. So I like this one right here because it crosses the grid. I'm going to call that 0.1. And you know what? I might take this very last one, not the data point, but a point off of the line itself, and I'm going to call that 0.2. Perfect. Now when I calculate the slope, slope is equal to y2 minus y1 over x2 minus x1. Well, let's see. Y1, I'll highlight this in red. Y1 was 2.5, and Y2 was 0. Well, that's some nice easy math. So that's going to be 0 minus 2.5, and we should include units with this. Those are meters per second. And then let's see, let's look at the times here. Maybe I'll use blue for the times. So that one is very clearly 10 seconds, and this one is 1 second. So back to the nice color felt pen. I've got 10 seconds minus 1 second. When I go through, plug in my numbers. Oh, there we go. There we go. So I've got 0 minus 2.5. Well, that's negative 2.5. And then I've got 10 minus 1. So I'm going to divide that by 10 minus 1, which is 9. Oh, my calculator's not turned on. There we go. So negative 2.5 divided by 9. This should be equal to negative 2.77. So 7/8, we'll round it to meters per second squared, because I've got meters per second over second, and you probably remember that from Science 10. So you might even remember actually what the slope represents. It's the acceleration in meters per second squared. But is that an appropriate title? Not really, because it's not showing you acceleration. That's what we're interpreting from the graph. What the graph is showing you is velocity as a function of time. Anyways, that is it. There's one more for you to practice and look at. Please make sure that you are good to go with this before we start our course. Anyways, bye for now.